Let's suppose that we have a rotating symmetrical object that is rotating about a symmetrical fixed axis. Now, earlier we said that if we want to calculate the magnitude of angular momentum of the object and the object's moment of inertia is constant, we can use the following equation. So the momentum of that particular object is equal to the product of the moment of inertia and the angular velocity of our object. Now, this equation gives us the magnitude of the angular momentum vector. And because it's a vector, it means it also has direction. How exactly do we calculate, do we find the direction of our angular momentum? Well, notice, for such an object, the direction of the angular velocity is in the same direction as the angular momentum. So these two vectors point in the same exact direction. And recall from a previous lecture, we saw that to calculate the direction, to find the direction of angular velocity, we have to use the right-hand rule. So let's suppose we have the following two cases. In case 1, we have the following symmetrical disk that is rotating in the clockwise direction. And in case 2, it's rotating in the counterclockwise direction. So to find the direction of angular velocity, we apply the right-hand rule. So we curl our fingers about the axis of rotation, we extend the thumb, and the thumb points downward, so that means the angular velocity and the angular momentum both point downward. On the other hand, if the object is rotating in the counterclockwise direction, we extend and wrap our fingers around the axis of rotation in this way. We extend the thumb and the thumb points upward. So that means for case number 2, the directions of angular velocity and angular momentum point upward. Now, knowing this, let's look at the following example. In this example, we essentially want to use this concept of conservation of momentum and the right-hand rule to calculate what the direction and magnitude of angular velocity is. Let's suppose an 80-kilogram person stands on the edge of a disc with a radius of 4 meters and has a momentum or moment of inertia of 2,000 kilograms times meter squared. Now, the person and the disc are initially at rest, and then the person begins to walk with velocity of 3 meters per second in the clockwise direction. So notice, this represents the linear velocity. Now, we want to find the direction and magnitude of the angular velocity of our disk after the person begins to walk with that linear velocity. So, let's apply the conservation of angular momentum because we're assuming the external net torque acting on our two objects is 0. So we have the initial sum of the momentum of the two objects is equal to the final sum of our momentum, angular momentum. So our initial angular momentum is 0 because our object is not moving initially. Now, after the two objects begin to move, we have the following case. So we use this formula. The I of the person multiplied by omega of the person plus I of the disk multiplied by omega of the disk. Now, before we go on, let's look at the following two equations. We're going to need to use these equations in just a moment. So we're going to make the assumption that the moment of inertia of the object is given by this formula. IP, I of the person, is equal to MP, mass of the person, multiplied by radius squared. And we are going to use this formula to represent angular velocity of the person in terms of the linear velocity and the radius. So omega of the person, P, is equal to Vp divided by R, where Vp is simply this quantity of 3 meters per second. So, we take this equation and we bring this term, the angular momentum of the disk, to the left side. So we get the following result. IP omega P is equal to negative ID omega D, where P is the person and D is the disk. So now we plug this quantity into IP and we get the following result. And now we solve for omega d for the angular velocity of our disk, and we plug in this quantity for omega p, and we get the following result. The omega of the disk, the angular velocity of the disk, is equal to negative of the product of the mass of the person, the radius, and the linear velocity of the person, and divide that quantity by our moment of inertia of the disk, which is given. So all these quantities we know, so we plug them in. 80 kilograms times 4 meters times 3 meters per second divided by 2,000, and we get negative 0.48 radians per second. So the magnitude of angular velocity is 0.48 radians per second, and the direction is opposite of the direction of the person. So for example, if the person is walking in the clockwise direction, that means its angular momentum and angular velocity points downward. But because the disk is rotating in the opposite direction by this negative sign, it's rotating counterclockwise. That means the angular velocity and angular momentum point in the opposite direction. They point upward.